Question 12, right? We're asked to choose the molecules that have tetrahedral electron domain geometry. Right, so right off the bat, we know methane, hopefully we know methane has tetrahedral electron domain geometry. So that's one correct choice. And because they're asking for electron domain geometry and not molecular geometry, right? Water as well has tetrahedral electron domain geometry. Boron trifluoride is trigonal planar. The sulfur hexachloride is, I messed it up, it's octahedral. I think the phosphorus pentafluoride would be trigonal bipyramidal. Yeah, phosphorus has got 5. And then it comes in bonds with the fluorines, right? Beryllium chloride. I will give you the table, right? The main table. Oh, okay, yeah. Beryllium chloride would just be linear. Right, so beryllium chloride would be linear in that case. Just the molecular geometry table. Yeah, right. So good question, right? There are 2 exceptions to the octet rule on the low side. Hydrogen will never have more than 2 electrons in its outer shell. Boron will never have more than 6 electrons in its outer shell. And it's because if we tried to fill the octet of boron, right, all of these fluorines have 6 valence electrons. If I dumped 2 of these electrons down to fill the octet of fluorine, that would form this fluorine boron double bond. And basically what that would do is it's going to create a positive charge on the fluorine and a negative charge on the boron. We don't want that. Whenever possible, we want to minimize charge. So actually the best Lewis structure of boron, right, is a structure where boron only has 6 electrons in its outer shell. So yes, boron and hydrogen are the 2 exceptions on the low side of the octet rule. Question 14. All right, question 14. A few of you are emailing me about this question as well. And again, it's just, I think, just the reading, right? So they're asking for the electron domain geometry, which in not every case is the same as the molecular geometry, right? So just be careful what we're asked for, right? So oxygen 1, right? Our electron domain geometry, I've got 2 domains. So our electron domain geometry, right, we'd be linear. Carbon 2, 2 electron domains, we're linear again. Carbon 3 has got 1 domain, 2 domains, 3 domains, 4 domains. So that would make it tetrahedral. Right, oxygen 4 has 3 domains. So 1, 2, and then here's our 3rd domain is a double bond. So 3 domains is trigonal planar. Right, we should also know the hybridization of those domains, right? So SP, tetrahedral, SP3, trigonal planar, SP2. And I think there's more to this question. I think there's 2 more. Oops. Yeah. Carbon 5, oxygen 6. So carbon 5, right? Carbon 5 is also trigonal planar. Right? It's trigonal planar because I've got 1, 2, 3 domains for carbon 5. And then many of you are emailing me about oxygen 6 because you're saying it's bent. Yes, the molecular geometry is bent, but they are asking for the electron domain geometry. The electron domain geometry, 1, 2, right, 3, and 4 total electron domains. 4 total electron domains makes this tetrahedral electron domain geometry. Again, so just be careful what you're asked for, right? We are being asked for electron domain geometry, so that's what we want to answer, not the molecular geometry in this case. So there's question 14. Yeah, if at the end, right, we've got time, I can do some hybridization examples of pi bonds. All right, so question 15 and question 16. No, right? Bent is not an electron domain geometry. Your 5 electron domain geometries are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Those are the 5 electron domain geometries. Within each of those geometries, we have more than one, except for linear. We'll have more than one molecular geometry. And so that's where bent falls in. Bent is a molecular geometry. All right, so choose the correct bond angles of atoms labeled 2, 3, and 4. All right, 2, 3, and 4, 2, 3, and 4. What's the geometry for 2, 3, and 4? Yeah, it's trigonal planar, AR. Yeah. All right, which is a good transition to this question because yes, atoms 2, 3, and 4 all have 3 electron domains, so they are trigonal planar as well. All right. So if we're trigonal planar, what should our bond angles be? All right, they should be very close to 120 degrees. Yeah. Right, we're sp2 hybridized. We've got 3 domains. So 3 domains, right? We've got a circle and we split it up into 3 equal quadrants, right? Those quadrants each need to be 120, approximately 120 degrees. Madison, it's the table I gave you, like it had been right before break. Right before break. And it's a table that we worked through that had all the geometries listed. Trigonal bipyramidal is BI, not BY. I mean, Emily, it works in this case because it's trigonal planar. It's a flat geometry. It doesn't work in every case. All right, question 16. It's just funny, like no one had any questions in class, and now everyone wants to know where we can find a table. Right, question 16 is asking for which one of these is polar, I think. Choose the molecules from this image that are polar and none that are non-polar, right? So polarity, a lot of you have asked about polarity, right? So we'll talk about it a little bit more here. What we need for a molecule to be polar is we need a lack of symmetry, right? We need an imbalance in the symmetry of a molecule. So this first molecule, for example, is non-polar, and it's non-polar because I have chlorine matched with chlorine. So chlorine is electronegative, but when it's in a tug of war with itself, right, they're 180 degrees apart. They basically cancel each other out. So because they cancel each other out, we don't have to worry about those vectors. Fluorine is also polar, but again, because we're all around the equator, these 3 fluorines basically cancel each other out because they're pulling electron density away, but they're pulling electron density away, right? Equal strength, and all those vectors cancel out. Whereas with molecule 2, you notice in molecule 2, we've lost that symmetry. So because we've lost that symmetry, right, here I've got fluorine matched with chlorine. In the tug of war, right, fluorine is winning that tug of war. So it's pulling electron density to the top of the molecule. And you'll notice we've got fluorine over here on this side also matched with chlorine. So again, that fluorine is winning against the other two chlorines. So in net, right, that makes this molecule polar because we don't have symmetry around the bonds. The same thing here for this molecule, right? These two fluorines are stronger. They're more electronegative than chlorine, so they're going to win out. And our net dipole, right, would be something in this direction, right? The front left quadrant of the molecule. Just like our dipole here would be something, we average those two vectors together. But our dipole will be something up here, like in the front right or upper right quadrant of that molecule. So that makes both of those polar, right? We started at 8:30, Will. I don't know. Right, so the molecule down here is also polar because again, right, fluorine is matched with chlorine, so fluorine wins. That makes this molecule polar. Here we have symmetry, so this molecule is non-polar. And then here, again, we're not symmetrical, so that would make this molecule polar as well. So we had a good question, right? Ashley wanted to know, how do I determine the length of the arrows? I'm kind of just drawing the arrows based on how electronegative each atom is. So fluorine is the most electronegative atom. So I'm drawing that arrow a little bit larger, a little bit longer than the chlorine arrow because fluorine is more electronegative than chlorine. So they're not really drawn to scale, but I'm just kind of using the arrow to represent basically which atoms are more electronegative and therefore which atoms are more strongly pulling the electron density toward itself. All right, that was question 15, maybe. Now that was question 16. So question 17, of the following species, which ones will have a bond angle of 120? Will we have to determine polarity with lone pairs? Polarity is mostly based on. Oh, okay, I see what you're saying. So I'll give you an example then to kind of answer your question. If we had like sulfur tetrafluoride, right? And okay, right, it's got 4 fluorines. So I think this is kind of your question. Do we have to determine polarity with lone pairs? Here's an example where you can determine polarity with lone pairs. Fluorine and fluorine, those two cancel out, but these two fluorines on the equator, right, they're pulling to the right side of the molecule, and there's nothing pulling the opposite direction because lone pair of electrons, they don't have electronegativity. So those two fluorines, they're in a one-way tug of war. There's nothing pulling back the other direction. So that would make this molecule polar because those fluorines, right, are pulling against just a lone pair of electrons, right? So I think that kind of answers your question. Yeah. The correct answer for 16, I think, was molecule 2, 3, 4, and 6.
John, come back.
All right, guys, I will be leading the rest of this review session. If you have any questions, leave them in the chat. Get started.
What's the answer to number 22?
A. The answer is A.
You a real one for that?
Thank you.
What you guys get for 23?
23 is 1.15, so B.
Let's keep this going. What do we get for 24 and 25?
25 is Boyle's law.
Both of them are D. Who has 19?
I have it. One sec. Okay, it's whoa. Wait. 18. Okay. The first one is SP2. The second one is SP2. Third one is SP2. The fourth one is SP3. SP2, and that's the last one.
Thank you.
You're welcome.
All right, I'm back. Sorry. What did I miss? Sorry about that. I don't know what happened. All right. Yeah,
Welcome back.
yeah. Thank you, Aaron. Somehow Zoom just like booted me. All right. Not really sure. 1 minute it was working, the next minute Zoom just shut down. It apparently can't handle general chemistry. It was too much. All right, so we were on. No, Connor. You don't all get 100s. You can still study for the exam. And then, yeah, Will, if you want to teach a question, you can go ahead. Yeah, a little bit late for that. So we're looking for 120-degree bond angles for this question, right? So the phosphorus trihydride. Yeah, we're headed that direction, right? So this one is in the tetrahedral electron domain geometry. The chlorine trifluoride is in the trigonal bipyramidal electron domain geometry. The nitrogen trichloride is also in the tetrahedral electron domain geometry. So far, none of these will have right 120-degree bond angles. And then last but not least, the boron trichloride, right? We already saw boron violates the octet rule. It'll never have more than 6 electrons. So boron trichloride is the only one here that will have will be trigonal planar and would have 120-degree bond angles. So choice D for question 18, for question 17, sorry. And then I think someone asked for question 19. So we'll do 19 next, but let me just stop this. It's D because it's asking for which one of these has 120-degree bond angles, right? So this is in the tetrahedral electron domain geometry. So this is going to be like 109.5. Same thing here, tetrahedral electron domain geometry, so in the range of 109.5. This is T-shaped, but it's within trigonal bipyramidal. So the electron, the bond angles here would be like 90 degrees. So D is the only one that would have, yeah, where it can make 3 bonds, like Todd said. So that makes it trigonal planar. Trigonal planar is 120-degree bond angles. All right, Aaron, I guess we can. For the molecule to have seesaw electron, oh, okay. So, the sulfur tetrafluoride would be a good example of this, right? Sulfur tetrafluoride is seesaw molecular geometry, but it has 5 total electron domains. So we've got 5 electron domains. For the molecule to have seesaw electron domain geometry, it basically needs to have 1 lone pair. For the molecule to have trigonal bipyramidal electron domain geometry, so that would be like the phosphorus pentafluoride. Right, I hope that exists. Yeah, that exists. So that's trigonal bipyramidal, so it must have 0 electron domain geometry. And then for the T-shaped, we just saw an example of the T-shaped, right? T-shaped was that chlorine trifluoride. For it to be T-shaped, right, we must have 2 electron pairs to give us that molecular geometry from the trigonal bipyramidal electron domain geometry.